3 minutos.
3 minutos.
André, Antônio, Daniel.
Helio,
Sim, yes.
perdi teu vídeo.
Fala. Eu sei.
Ah, tá bom.
Voltou o vídeo aí?
Voltou, Helio.
Ah. Sérgio, Roberto, Ranier, Luiz Alberto, Fernanda Lopes, Daniel Anthony, André Alejandro. Então, um bom número. Tá? Dois minutos.
2 minutos. Um minuto. Bom, tomara que tudo isto passe logo. Ano que vem, novamente, provavelmente vamos ter o evento novamente. E aí, talvez poderíamos ter minicurso, outro minicurso ao vivo, né?
Ao vivo acho que é melhor, né? Porque
Com certeza, é bem melhor.
a gente pode interagir melhor, essas coisas complicadas fica mais fácil na hora.
Fica. Sim, é complicado, é. Mas são os tempos, né, que estamos vivendo aqui. Tomara que tudo melhore, logo.
Talvez, se pudesse ter antes uma preparação em quântica e relatividade, facilitava.
Sim, claro.
Opa! Quase 10, está na hora. Time.
Pronto, ok. Só um minutinho, olha. Botar para gravar. Okay. Welcome everybody to the last lecture of this mini course on Feynman diagrams. So I hope you are enjoying this course. Any question you have about anything about the course, of course, please send an email to Helio. And later I'm gonna post on the chat room 2 forms in order for you to fill out. These are the attendance forms. Okay. What else? I think that's it. Okay, Helio, please, whenever you're ready.
Okay. Good afternoon, everybody. So today I plan on finishing this very, very short mini course, and the idea since the beginning was that we could be able to at least make a calculation of a Feynman diagram. So we have to go through all those quite difficult, some points, some equations just to figure out how to work. But today I'm going to apply those links and calculate for a simple Feynman diagram. So let me start sharing my screen. Okay, that's 3, 2, and 1, and now probably now you can see my screen. And as usual, if you have a problem, I ask the organizer just to send me a message. Let me see, go to, okay. So as Professor Kashimoto has said, today is the 25th. So yesterday I must apologize because my Apple Pencil started failing miserably, and was very complicated, very hard to write because it kept failing. I hope this will work fine today. If it doesn't, I have another software that I will try another software in case there is a problem. So anyway, today is the 25 September 2020. Okay, as in Lima. Again, I am writing here my email. So, as Professor Castromonte said, please send me email with your questions and doubts. It's better by email because then I have time to give a better answer than just during the presentation at cbpf.br. Okay? Okay, so I want to write just for our reference things that will be important and then we need today. So at some point, there's a very strange equation that came at the end, has some matrices. Let's write them here. So this is gamma. This gamma matrix is just 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. Okay? The other matrix is 1, and is 0, 0, 0, 1, 0, 0, 1, 0, 0, minus 1, 0, 0, minus 1, 0, 0, 0, 2. So although they are 4 by 4 matrices, note they are full of zero, lots of zeros in this matrix. So when we make a matrix multiplication, it will be very easy, very simple, because most of the terms are 0. So it's not a big deal, not very difficult to make any calculation. So we have also what shows sometimes that is shown, just change the color now. We have the J. This is another matrix that is just 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. So this matrix is, when you multiply this matrix by a vector, basically what it does is to change the signal of the third, second, the third, and the fourth component. That's all it does. Okay? Just reference, let me have the, just for us not to forget, those here are the Dirac man. Okay? And all the measures that are important are the okay, and those are the Pauli. Note that we can write this gamma matrix as arrangements of the Pauli matrix. That's what's done sometimes. Okay. The other thing that we got yesterday are the equations representing the particles that we have to work. So we have the C squared, and then C px plus I pz over E plus mc squared. Okay? And the other one would be U2 C px minus I py E plus mc squared and C minus pz E plus mc squared. Remember that mc squared that shows is the rest energy of the particle. So the energy that a particle has when the particle is at rest. And the E is the total energy that is a function, depends on the movement, the speed of the particle. Okay? Pz, Py, and Px are the x, y, and z components of the particle momentum. And if we make a very convenient choice of frame of reference, we may have the particle just go in one direction, it will be the z direction, so Px and Py will be 0. Okay? And these two equations here, they are for energy equal to m2 c4 plus p2 c2. This is the energy equation, the relativistic equation relating energy and momentum of a particle. Okay, and this is positive. And you have two other equations, two other U, writing here just for thing to be complete. That would be U. U3. Again, this plus MC2. Okay. Here we have C E MC squared. And then we have C px plus IPy E minus mc squared, 1 and 0. And finally, we have the fourth one, mc squared. And this is going to be C px minus IPy E minus mc squared C minus p z E minus mc squared 0, 1. Okay, and those two is for the situation where the energy is negative. Okay, so the situation of negative energy was interpreted as the antiparticle. Uh-oh. That was wrong. Okay, as the antiparticle. So rather than having this situation where you have equations with negative energy for the antiparticle, we have a particle with negative energy, we are considered that to be antiparticle with positive energy. So what we're going to do is rather than is writing the equation, so rather than having solutions the U3 and U4 with negative energy, whatever that we will work this as we're going to use solution of antiparticle antiparticles with positive energy. So we're going to use only the first two equations here, what's called U1, U2 for particle. And the other two that would be for negative energy will be replaced by what we call V. V1. We have the normalization exactly the same. We're just C, then will be Px minus IPy. We get this just by replacing the energy by minus the energy, the momentum by minus the momentum. E plus mc squared. The other one is C minus pz. E plus mc squared, 0, 1. And the other one will be called V2. Again, the same thing. C, PZ, E plus MC2, C, PX plus I, PY, E plus MC2, 1 and 0. And in both cases, the energy is equal to M2C4 plus P2C2. Okay? Now, that's pretty much all we need. And if we orient the z-axis along direction. Of motion. Then Px equal Py equal to 0. That's exactly what we're going to do. Make things much simpler than we do. And something that's important for us to do, that's going to show in the equation, this has to do with the relativity, and we don't have time to go into details, but then if you have something that's a U, that's A, B, C, D, so 4 components, we're going to have what's called U bar, that will be just A, B, minus C, and minus D. And consequently, the same goes for a V. If you V, C, D, E, F, G, H, we're going to have V bar equal to E, F minus G minus, that's all. So you just replace the two last things. Okay, then we are ready to solve a Feynman diagram. Okay, let's finally, let's solve, let's calculate M for a Feynman diagram for quantum electrodynamics process. Okay, yesterday I listed the Feynman rules. Okay, I'm not going to repeat it completely here, but I can just, if you remember well, we have system, you have things going into and out. Okay, and for each particle, you have to define the momentum, and in the case, the spin. So let's see what's going to do with the following event. An electron interacting with a muon, producing the electron and the muon. That's the electron muon scattering. Basic situation, we have one electron and muon, and they scatter from each other. Okay? Okay, what would be the simplest Feynman diagram for this event? We're going to have, say, here I have the electron, and here I have the muon. Okay? They exchange here photon. We're talking about quantum electrodynamics. And here we have again the electron and the muon. Okay. So if you compare to this idea here, in this case we have two particles coming into the process, the electron and the muon, and two particles leaving the process, the electron and the muon, and they exchange a photon in there. So we need to write down all the quadri-momentum. The quadri-momentum is a combination of the energy and the momentum of the particles for the electron and muon. So I'm going to call them, let me use this color here. So this one here, I say that it has the momentum P1. Okay, so the spin of this particle will be S1. S1, just to say that the spin of the first part. B1 here will be the quadri momentum will be P2, and the spin will be S2. This one will be momentum P3, and the spin will be X3, and P4, and S4. All this is arbitrary. Of course, I could call any one of the particles 1, 2, 3, or 4. So this, for me, this is particle 1, this is 2, this is 3, and this is 4. Okay? No particular reason to follow this order. And here we have the gamma. And for the gamma is the one that connects. You also have the internal momentum. In this case, we call it Q. Okay, so that's basically what we do in the first step of the Feynman diagram. Okay, and as I mentioned, the Feynman diagram rules. No? For the external lines, we have something that is approaching, getting into the vertex will be U. And something that's leaving the vertex is going to be the U bar. Okay? This is for particle. Say the particle. And in the other case, wait a minute, something here as well. Okay, so the antiparticle, remember the antiparticle is moving backwards in time. Okay, so this will be the antiparticle. For this particular process here, you have only particles. You have electrons and they have muon. So you don't have to be concerned with this V and V bar. Okay. We also see that for each vertex, we should add a factor, for vertex. Each vertex. For each vertex, we have a factor that's I, GE is the intensity, the coupling of the interaction, and gamma, me. Remember again of those functions that I have just written here at the beginning. You have number 0, 1, 2, and 3. You see when you make all the assembly that we need all of them. That's for each vertex. And in this case, here, 2 vertices, right? I call this vertex 1. And this vertex 2. Okay? And then we have remember that the G in the case is equal to E, the electric charge, 4P. Okay, so basically it depends on the electric charge, the fundamental electric charge of the electron. But we're going to just call it GE, just make things simple. At some point, if you need to really replace by a number. So this for each method. And then we have the propagation. In this case here, the propagator is only this photon here. Okay. We have only 2 vertices and this photon between them. So for each propagator, since the propagator here is a photon, as you see, okay, the photon here. We now have a factor that's minus I, J, mini, so Q square. Q square is from the momentum of the photon. It's transferred there. And G mini is, again, this thing here at the very beginning. This one here. So it's a very easy matrix to make a multiplication. So it will be easy, not a big deal. And remember this matrix here, as I said before, the only effect of multiplying this is change the first, you have the first line and column. Okay, so you multiply the first line for the column, then the second line for the column, the third line for the column. So the effect of this is just to to keep the first elements and change the signal of the other three. Very easy. So here we have this, okay? And then we have the conservation of momentum. Then you have energy and momentum conservation. That was 2, 5, 4, K1, place K2, place K3, where this is made for each vertex. Each vertex, no matter what the Feynman, has only 3 lines. Okay, one line arriving to lines leaving. So let's, and then after that we integrate. Over the internal momentum. In this case, there is only one internal momentum because the only internal thing is the photon going from vertex to the other vertex. Okay? So at the end of this, we have the M, the amplitude loop is equal to minus I base result. So let's apply all this to this thing here. So let's go very carefully. What you do? We'll start from coming from backwards. We start from this point here, moving that way, and we follow each line. Okay. Just to help us to remember. Me. This is, I call 1, 2, 3, and 4. Okay? So let's apply the Feynman rules here on the things we have. So I have here, out here, 2, 3, 4. Now, do it very slowly. You have U bar S3 P3. Okay, we have here we have P3 S3. So this particle here that happens to be an electron, but doesn't matter, has the momentum quantum momentum P3, and this is a spin that's called S3. Okay, and since this is a particle, right? So if you go here, it's a particle. It's a particle leaving a vertex, so it's a U bar. Okay, that's what I have here. The U bar. After that, you're going to have I, G, E. This is vertex. Okay? I'm coming this way. Okay. So I have this line here, that was that part of the U bar. Then I have the vertex 1, and then I have the second particle. The second particle here is also a particle, and see, it's going toward the vertex. Okay. Where is it? Where is it? Toward the vertex. Towards the vertex. Okay? Towards the vertex is this one here. So it would be U. As U. And in the case of the particle 1, so it would be S1 and P1. Okay? That's for the first line. Then I have to repeat it for the line that of the muon. This is for the second one here. That's what you have to do. Again, if you come from right to left to muon, but it's a muon leaving. Again, It's a mu. It basically reproduces the line at the top. But now you have the particles 4 and 3. Everything else is pretty much the same, right? So, before that, okay, let me write the propagator. Now let me write the propagator minus G. No, let me write this better this way. Minus I G mini. That's the matrix. We have that Q square. Okay, and this is the propagator. Of course, I could have the propagator first. That doesn't matter, but that's okay. And then for the second line is pretty much like the first one, but rather than having P3, P1, we have P4 and P2. So it would be U S4 P4. Now the vertex. And this is for vertex 2. And then U S2 P2. And then all the other things for the conservation that's there. 4 P1 minus P3 minus Q. This is for vertex 1. Okay, if you go here to vertex 1, here in vertex 1, you have P1 get into the vertex, and leave you have P3 and Q. For conservation of momentum and the energy, P1 must be equal to P3 plus Q, meaning P1 minus P3 minus Q equals 0. The ones that arrive into the vertex are positive, the ones leaving the vertex are negative. So P1 minus P3 minus Q. And of course, we have the same for vertex number 2. But vertex number 2, you have S2, in this case, both are arriving here, and then P4 is one leaving. Of course, I could do the other way around, right? Because it's supposed to be going both directions. Doesn't change. And P2 plus Q minus P4. This is for vertex 2. And then the T for Q. Okay. Now, remember, this expression looks terrible, but it's really not terrible, because now we have to integrate. We have to integrate on this D4, the quadrant momentum here. But remember that we have here delta function. And it's always good to remember that when we integrate something, we have a delta function, say x minus a, there's a function s, dx, doesn't say integrate. It doesn't matter what the f function is. So fx could be a very complicated function. The result of this would simply be f in a. So all we have to do is to get this function f. Is the value of the function for x equal to a. So in the point where the delta function has the argument 0. The argument 0 is exactly when you have the conservation of momentum, right? Because here you have a delta that assures the conservation of energy and the momentum. See, this delta here will be 0. It's going to be 0 if P1 minus P3 minus Q is not equal to 0. So they are not equal to 0 means that there is no conservation of momentum energy. So this process doesn't happen. This is 0. And that's the end of this game. And the same for the other vertex. So to integrate in the Q2, we just have to see a point where Q is equal to one of the functions. So integrate. So this will be, that means, in our case in here, Q equal to P1 minus P3. Okay? Here. We have to P1 minus P3 minus Q equals 0, means Q P1 minus P3. So all we have to do to integrate all these things is to replace the Q, make Q equal to P1 minus P3 in the other terms of the equation. And it means here, that's where Q is present. Okay? And of course, here. So the Q will disappear for the equation. And you have equation only with the momentum, the quasi momentum of the particles getting into and leaving the person. So if you do that, I'm going to have 2 P to R 4. Here you have S3. I keep repeating S3 and P3 just to make clear what you are doing here. Okay? Then we have I, G, E, E, Q, S, 1, P1, minus I. Here we have P1 minus P3. Have Q anymore. Then here is S4, the spin of particle 4. And the quasi momentum of particle 4, I, G, E, again, U, S, spin, particle 2 with its spin and its momentum. And what was left is a delta function here. It will be P2 plus P1 minus P3 minus P4. Note this delta function, P1 plus P2, plus P2 minus P3 minus P4 is equal 0 for P1 plus P2 equal to P3 plus P4. So meaning that this is true, that's not 0. Otherwise, sure, difference is 0. Effect equals to 1. Let's see. So P1 plus P2 equal to P3 plus P4. So this is a conservation of the quadri momentum. That's exactly what we have here. See? So the quadri momentum here and the P3 momentum and the energy means the P1 plus P2 must be equal to P3 plus P4. And that's exactly what it shows here. Yeah? For any situation, any case where P1 plus P2 is different from P3 plus P4, the delta function is equal to 0, and all this disappears. So there is no amplitude, no M. That Feynman diagram does not represent anything that could happen. So once you have this, the game now is just to get rid of the delta function, because we are showing in our problems we have shown that the energy and momentum is conserved. So this is going to be I G E square, okay, because you have G two times G here, G and G, and we have I and the I. So I times I is -1. With the minus, then we have only I here. I is the imaginary number, don't forget that. So you have I G E square. You have P1 minus P3 square. And then, again, now we have U bar S for P4, the gamma, U S1 P1, the particle one, which is its spin, this quasi-momentum, and the other one is U bar S. He's wrong. He's S3. Sorry, this is. He's S4, P4, gamma again, and the U S2, P2. Okay? And we know that this has to be equal to minus I M. M is what I want to calculate. So M, I'm going to put it here in red. Is equal to minus GE P1 minus P3 square U. I'm just going to write U3 just to make shorter. And then 4 U2. And this is the amplitude of the Feynman diagram that we have been looking for several days. But wait. You're going to say, Helio, you are cheating us because there is no number here. You just have an awful expression where they have these U bars and gammas, and we really don't have a number. Okay. Now let's then put numbers in there. Now, for a real situation. Okay, what will be the real situation? Let's do the following. Let's solve it. Oh, okay. Let's solve it. Of course, in fact, if you decide to calculate this for a general case, it's really complicated. But if you can get a particular situation, so let's solve it for the case. Okay, we have E plus Vman going to M plus Vman, as we have now. But say I and U minus approach each other. Along the zx. Remember I said that we're going to define our frame of reference in a way that the parts are moving in the z direction, z intersection. So we have the electron and the muon that are coming to each other. So they are going to collide, let's say this way, head on. They are moving. Okay, so they come head on, and then and then it's awful. And then repel and return back along the zx. So they come together and they repel each other and go back all in the zx. And all particles have this is a complicated way. That's meaning that their spin is in direction of movement. Okay, so the situation we're describing here is the following. I have an electron coming this way. No, I don't want this color. I want this to be in blue. I have an electron coming this way. Okay, so this is the electron. Okay, and the spin of the electron is in the same direction, so the spin is this way. Okay, so if you consider the spin like a intrinsic rotation of the electron, it's spinning this way. That shows here. And then we have the muon. The muon is coming in the same direction. So they will collide head on. So this is the muon. Right? And since the spin is also elliptic, is also going the same direction, so the spin will be this way. Okay? So this is in our Feynman diagram. In our Feynman diagram. Remember? This is the particle 1, this is 2. And so this is particle 1, and this is the particle 2. So, they collide. Then, after this, and here is my x, my zx. Zx. They both come along the zx, and they will collide. They say after the collision, after the interaction, they will go back also along the z. So here we're going to have the neutrino, the muon, sorry, and here we have the electron. And I'm saying here that in all situations the helicity is 1. In all situations the spin goes in the direction of movement. So here we have okay, and this is the particle 3 and 4 here. So here we have 3 and here we have 4. Okay, now in this situation here I have px equal to py equal to 0, because we have defined the problem. Okay. Now, if you remember, you don't have to remember, I have it here within somewhere. At the very beginning. These are the U particles, right? Oh, these are the U particles. Because remember the equation, that formula you got for the M, you have the U and the U bar. So there's the U. Huh? So remember, you need here the C. You have here C, PZ, so, and here, see, C, P with Z. And here you have the PX and the PY. So PX and PY are 0 now. So this fourth terms here, the fourth component is 0, simple 0. And here we have PZ, but remember, since the way they define the problem, all the momentum is in the PZ direction. So PZ is just the modulus of the momentum. So here when we have a C times PZ, you just have the C times the momentum of the particle. That's exactly what we're going to do here. Gosh, my goodness. And C, PZ is just C times the PZ. But remember, and pay attention, in one of the cases, for the particle number 2, when they are going to collide before the collision, we have, since I defined the way I defined the z-axis, the z component of the momentum of the electron is positive. For the muon, the z component of the momentum is negative because it's going in the negative direction of z. And when they leave, so after the interaction, you have the momentum of the particle, so the P4, the component z is in positive direction, and for electron, the component is in the negative direction. So there is to be a plus and a minus sign. But anyway, CPZ is it, and then remember, because we have from relativity, we have that E square of energy is the square of momentum, quadrimomentum, C2, the 3 moment C2 minus. In fact, here I have P square, but the P is a vector, so it should be a vector square. What's a number anyway? Plus M 2 C4. Then P2 C2 is just E2 minus M2 C4. That's exactly what we. Then the momentum of P times C is just the square root of E2 minus M2 C4. But this is something we know, right? This kind of mathematics. Remember that, let's have this in red to make call. If B equals A plus B multiplied by A minus B. Okay? And that's what we have here, okay? We have a square, E square minus B square, MC2 square. So, yeah, fine. So now let's write the expression for U in U bar. Remember? So U equal to N, that normalization factor. My goodness, the Apple Pencil is failing again. My goodness. So here we have 1, 0. Then I will replace all that for that expression here. It will be E minus MC2 E plus MC2 E plus MC2 and 0. Okay, it's nicer this way. Okay, if I replace N by its value, that's written there before, this would be see, here will be 1, 0. This is just algebra, okay? M C2 E plus M C2 and 0 here. So making all this simplification, all this multiplication, you simply have that U1 is no. No, nobody's calling me. 0021 is here. So U1 over C E plus MC square 0 E minus MC square and 0. Now, so this is quite simple. This is not a big expression. Okay. Now let's make it even for another simplification. Let m equal 0. So let the mass be equal to 0. You're going to say, oh, come on, the mass is not 0. Okay, the mass of m equals 0 is much bigger, the mc2. Note here, what you have the square root, and inside of the square root you have e plus mc2. mc2, remember, is the rest energy of the particle. But if the particle has very high energy, so the particle is not still, it's moving forward. So you're going, okay, if the energy is much higher than that, so the particle has lots of kinetic energy, I can just ignore this mc2 term. I mean, let's make things easier. Example, accommodations to make, because most times we really have parts of very high energy. So if then I'm going to have it red, but that's it. Then the U one simply E over C. Here you have 1, 0, 1, 0. Very, very simple. Okay. Now, if you do the same, I did this for one of them, let's say U1. You can have to do the same for all them, right? All them. So, all the 4. So, following the same. Following the same. For U2, U3, and U4. So the 4 particles that you have, we're going to have the following. The U from particle 1. I have stopped writing S1, P1. For the particle 1, I'm going to have G, 0, 1, 0, 1. One, 0, 1, 0. Okay? This one, let me make the drawing again for the Feynman diagram. For my particle, I have, not the Feynman, I have E, me. This was 1 and 2. And then we have 3. Okay, and here we had, I'm just repeating this one here. Okay. Now, okay. Now, pay attention. That's meaning that P is equal to minus P. Okay? Okay, then we have all the 4 components we need in that expression. The U for the first particle 1, the U for particle 2, for particle 3, and particle 4. And as a consequence, you also have the U1 bar. It will simply be 1, 0, minus 1, 0. Okay, 0, 1, 0, minus 1. You see? 0, 1, 0, minus 1. 1, 0, minus 1, 0. Okay? Now all I have to do is to apply this to those equation that we have there. I have to do it here. What is the expression? This is the expression, remember? Now we have U1, we have U2, we have U3 with bar, and U4 with a bar. And all the other values just replace there. And let's see what happens. Okay. So then let's apply to the expression. Okay. Now we must be careful. Okay. The expression M is minus GE now you have 3 gamma 0. Now I'm opening that expression, okay? Remember, I told yesterday that in the equations would, rather than use a sum that makes things very complicated, use that convention that was invented by Einstein, that when you have repeating index, you just add the repeated ends. Then here is the gamma, you have gamma 0, gamma 1, gamma 2, and gamma 3. So we have to make a lot of them. So here we have, no, this is wrong. Here is minus, then we have now is gamma 1, U 1, gamma 1, U 2, minus gamma 2, U 1, 4, gamma 2, U 2, minus the last one, that's U 3, gamma 3, U 1, 4, gamma 3, U 2. Okay, this is not really difficult to calculate, because remember, most of those matrices there are just full of 0, 0, 0, 0. So let's do one by one. Let me get to my paper here so I don't get more confused than I have to. Where is my calculation? Hello? Hello?
Professor, you are using the G matrix because you change the minus.
Yeah,
just change.
Exactly. Yeah.
And I suppose that the G matrix. And I suppose that the G matrix is between in before
here, this one.
When you calculate the amplitude, in the middle, I suppose that the G matrix will be stay.
Yeah, but they disappear. See, this is the G matrix. You see, it keeps the first one, okay, and it changes the.
Yes, the first is positive, the second. Okay.
Yeah, the second, the third, and the fourth are replaced by minus whatever it was before. So that's what happened here. Let me see if I find thing. It's simplicity here, okay? Where is it calculated? I'm not going to find here. But anyway, where is it?
We are in the limit, and the momentum is bigger than the risk mass, yes?
Yeah. So here's the G matrix, okay?
Yes.
Change the thing. That's what happened. Sometimes this is not even mentioned because that's something comes from relativity. When you have a quadri momentum or a quadri whatever, let me see if I can write it here briefly, just for people not to get lost. So if you have a momentum or a vector, let me call it a vector, not to make things more complicated. If I have, say, a vector, say a vector A that is, my goodness, basically AX, my goodness, AX, say I plus AYJ plus AXZ K. Okay, and we have, if you want to make A square, you just have AX square plus AY square plus AZ square. Okay, that's very good. But when we are dealing with the relativity, what we have is a quadrimomentum, a quadrivector. The components will be, say, the x0, x1, x2, and x3. Okay. Now, the thing that we're doing here basically are dealing with the, say, the modulus of the vector. Okay. And if we have the Galileo transform, this modulo of this vector does not change with the transformation. Okay. The corresponding thing when it comes to relativity is similar, but unfortunately, what you would going to have will be something like S0 square minus S1 square plus S2 square plus X3 square. Okay, so it's almost the same, but not exactly the same, because there is a negative, or if you just open this, is minus S1 square minus S2 square minus S3 square. So the way to deal with that, exists what they call covariant and contravariant forms sort of thing. So one would be, say, x0, x1, x2, and x3. And the other one would be S0 minus x1 minus x2 minus x3. And when you multiply these two products, you see line and the column. There is just one line and there is just one column. When you make this multiplication, like magic, what you have is exactly S square minus x1 square minus x2 square minus x3 square. That's exactly what you want to do. So we have this covariant, one's covariant, the other contravariant. Notice that's exactly what's happening here, right? The U bar, the U bar is that thing that I just changed, and the U is like that. But in the case of these spinors, it's not, the transformation is not like that one. You have to, it's just, you move, as I said, if the U is A, B, C, D, and in this case it would be A, B minus C minus D. It's different. There's no point in trying to solve why. But that's what we're going to do, what we're doing here. And that's why when you have this operation here, because of G matrix that's there, the first one that corresponds to the x0, let's say, the first component, is still in the positive form, and the others all come with a negative sign, negative sign, negative sign. This is part of relativity. We don't have time to see that, but anyway, at this point, I have just to accept that's how it operates. Just use that G matrix is there, and that's the result we have. Okay? So,
okay, Professor, yes.
I know that's okay, but it's easy to make the calculation because there are lots of ones and zeros. So let's do it one by one. It's not a big deal. Let's do the first one. So let's do it. Let's start with the first one, that is for the gamma 0, okay? The gamma, we have this factor before, but they are just similar. So let's do it. So for gamma 0. So let's do it here. We're going to have basically, again, this U1, gamma 0, saco. 3 into 1, 4 into 3. The 1. Yours is 4. Let me see if I got it right, because this 3 and 1, 4 and 2, it's correct. Huh? So, where is the here you're gonna have basically this x, see, and then the u bar 3 is 0, 1, 0, minus 1, and the other one, the gamma matrix is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1. Multiplied by the other one, that's E. See? What is the 1? 1, 0, 1, 0. If we make this multiplication, you're going to have E. See? And this is 0. Okay? This is 0. So, since this is 0, no reason to make the second part. This is 0. Okay? So for gamma 0, the result was 0. Now let's do it for gamma. Ai, céu. Que saco. Let's do it for gamma 1. For gamma 1, we're going to have 1, 3, let's do B. This is the gamma 1 matrix. Minus 1. And the second E. And if we make this calculation, it's very simple. In this case, we have 2E over C. Yeah. And then I have to make, so, for the second term. And for the second, for you find the same thing is equal to 2E sub C. So, this term here, then this term here, the total is 1 times the other one will be 4E over C. Okay? Now, it have to do for the gamma 2. If we do the same for the gamma 2, it's the same expression. You're going to have E over C. And then 0, 1, 0, minus 1. This is always the same. Huh? Now we have the gamma 2 matrix. That's 0, 0, 0, minus I, and 0, 0, zero, 0, I, 0, and then 0, I, 0, 0, 0, 0, and minus I, and here we have 1, always the same, 1, 0, 1, 0, and again the E over C. Okay? So if we make this calculation, the result will be 2 I E over X over C, sorry. It's for the first term. The second term, and for the second term we have see, again, the same thing. 1, 0, minus 1, 0. Again, the matrix here, that's 0, 0, 0, 0, minus I, 0, 0, I, and 0, 0, I, 0, 0, minus I, 0, 0, 0. And 0, 1, 0, 1. And E, let's see. And if you make this calculation, the result will be minus 2I E C. So multiplying both, then if you multiply both, what you have is 4E squared over C squared. Okay? So, and finally, for the last one, and for gamma 3, we're going to have E over C, 0, 1, 0, minus 1. And here you have this gamma 3 matrix. This is 0, 0, 1, 0, 0, 0, 0, minus 1, minus 1, 0, 0, 0, 0, 1, 0, 0, is 1, 0, 1, 0, E over C. And again, this is 0, right? And you multiply the matrix, this is 0. So no reason to make the second term. Then, so M is equal to minus GE P1 minus P3 square 0, that's what's there, minus 8 E2 C2. So I'm adding all parts together. It's equal to minus G E square 8 E P1 minus P3 square C square. Almost done. Okay, so this is expression for M. Okay. However, as I mentioned before, you are dealing with quadratic momentum. And what we call P1, that's the way you write, is quadratic was the first term comes from with the energy, and the second itself is the 3 momentum. And of course for P1. And for P3, it's exactly the same thing. Okay? Because they are in the opposite direction. If you do that, then P1 minus P3 is equal to this first term here that depends on the energy disappear. It's 0. And then have 2P. And then P1 minus P3 square will be 0 square minus 2P square. as I said before. The first is not like in Galileo. It's minus 4p squared. And we know that E, as I said, is equal to P2, C2. That's relativity again. Minus MC4. This is equal to P. This is equal to P times C. Because, remember, because we consider M equals 0. That's the approximation we did at the beginning. So, replacing there, we have the M is equal to 8 GE squared E2 minus 4 P2 C2 equal to minus 2 GE P2 C2 P2 C2, what gives the result that the amplitude we're looking for is minus 2 GE squared. Okay, all that big expression at the end was gives us just a number. And then we can replace the GE by the intensity for the number that corresponds to the electromagnetic interaction, and it's a lot of work, of course, but it's at the end it's not that complicated because matrices are full of zeros, so the calculation is easy. Things get more complicated because the way I simplify the problems that I had, remember I had electron and the muon coming toward each other, and then the electron and the muon on the opposite way. Of course, there are many possibilities. When you have the electron and the muon, and the beginning of the situation is okay because I will always put myself in the center of mass reference. So we always be going one against the other. But once they collide, well, it's perfectly possible they may go in many different directions. Maybe the real result will be something like that. No? It is so although in this case here you have Px equal to Py equal to 0, here you have the Px, in fact, will be P and the Py will be P sine of theta. And the same for the electron, whatever. So you have all the possibilities because it may also happen that the result may also be something like that. So it could be, maybe the electron is the one that goes in that direction. Maybe the electron goes there, and the muon goes here. But anyway, you have a theta angle. So this, of course, makes the calculation more complicated because in this case here, see, you cannot make the approximation that Px equal to Py, what simplifies a lot the solution. Also, in this particular case, I said that they come this way, and their spin all this way. And when they leave, I say they also leave with spin in the same direction of the movement. But that's may not be the case. Maybe I have I may have a situation like that. I may have the electron, okay, and the muon, and I may have the situation, or yes, okay, and here we have this, or So we have all possible combinations. We have we have 4 possible combinations for spins, and we have all the possibilities of theta. What makes calculation much more difficult? It gives us lots of work because you cannot make the simplifications you made with px and py equal to 0. And of course, I'm considering that mass is 0 because I'm taking that the energy is much higher, so the simplification is possible. Of course, this is not always the case. You may have both interacting and leaving. Yeah? When they exchange energy, maybe at the beginning the electron had lots of energy, so its energy was much bigger than its vast mass. But once they exchange the energy with the muon, maybe the electron energy goes to a value that's not that much bigger than its mass, and then maybe I cannot consider. So if you don't make this consideration, I have to deal with that expression, that the square root of E plus or minus mc squared. But again, in the real problem, maybe you can do is just rather than use E, M, and C, just put the real values. What's the energy? The energy is 10 GeV or 15 GeV or whatever the value, and then just to work with numbers. That makes the calculation a little bit easier than have everything in numbers. Okay, this finished with my what I plan to show you. So at the end, we were able to calculate one Feynman diagram, a very simple one. Of course, if now we go to weak interaction, the procedure is pretty much the same, but in the case of the weak interaction, the propagator would be a W or a Z, and the W and the Z have mass. They don't have zero mass as the photon. So the equation for the propagator is a little bit different. It takes into consideration the mass. Depending on the situation, again, you may disregard the mass, but make things more complicated. But the process is the same at the end. If you get the books that I mentioned to you, the Mark Thompson book at the very end, it shows all the possibilities, all the basic Feynman diagrams, all the basic Feynman vertex, and the expression for the propagators and the expression for the particles. And it gives more work, but the principle is the same. So Feynman diagrams are interesting. It simplifies a lot of the calculation. It doesn't mean that's simple or easy, but anyway, that's life. Okay, I'm finished this mini course now. I hope that despite of the difficulties, it gave you all the opportunity to get some light on this process of Feynman diagrams, and you see that it's really possible for Feynman diagrams to get some information. Okay. Are people still there? People have given up?
No, I think they are there, Helio. Okay, guys. Helio, I really want to thank Professor Helio for the lecture he gave us on Feynman diagrams, and many thanks to
and
all
again,
of you.
Just to interrupt you a little bit, please don't forget to send me questions or if you feel something is not clear. I'm sure that many of things I talk are not clear. Just send me email. By my mail, I try to answer the best possible way. And again, before Professor Castro finish, I want to thank you the opportunity for this presentation. I hope next time and maybe next year I'll be able to be in person in Lima to have some ceviche.
Yeah, okay? Of course. We'll be happy to have you here.
Professor Castro, please. It's your turn now.
Okay, thank you, Helio. Of course, we'll be happy to have you here next year. To have for another course. As I was saying, I want to thank you for the lectures you gave us on Feynman diagrams. I also want to thanks to all of you guys for attending this course. I really hope you enjoy the course. I would ask some virtual applauses for our speaker, please. Okay, so as Helio said, please, if you have any question, please send him an email. Probably you'll get our answer. Okay, and I don't know if you have any comment or whatever, please.
No, I'm done. Thank you very much.
Okay.
Send the question, your question. I'll try to give an answer. Possibly, I will try to give a right answer if possible.
Okay, thank you, Helio. Thank you very much. And thank you guys. Okay.
Gracias.
Gracias a todos. Todavía tenemos un día más de evento, así que, por favor, todos están invitados a continuar. Todavía tenemos un día más del evento del encuentro de física. Después les vamos a, ¿no? Por favor, si ustedes tienen algún comentario para poder mejorar estos cursos, por favor, mándenos un email. Ustedes ya tienen el email del evento. Por favor, escríbanos. Así podemos mejorar, ¿no? Constantemente. Y aprendemos también nosotros, ¿ok? Muchísimas gracias a todos ustedes. Tengan muy buenas tardes. Cuídense bastante.